All right, welcome to Friday. We're going to be doing set, unordered set, map, and unordered map today, as well as an introduction to TDD, which is called test-driven development. We're getting a new assignment today. You sure are. It's in fact already in your homework directory. It's called fizzbuzz_TDD. And you transfer this semester. It's still going to take 26 from Chrono. Yeah, if it ends up being online, which I don't know if it will or won't, you might be able to take it anyway. I don't know. Okay, so yeah, let's do this. So the difference between a map and a set. Let's go with that first. Oh, we don't have the main indices. Perfect. Okay. I like to start over from scratch rather than using the end product of last semester's code, last period's code. Okay, so let's do this. We're going to talk about 4 data structures today. There's map, there's set, there's unordered map, and there is unordered set. And then there's also multi-map, multi-set, unordered multi-map, unordered multi-set. 8 different variants of what are very similar concepts. So what are the main differences? So between a set versus a map, which one should you use? Well, under the hood, a set is a BSD. So it has order logN, insert, search, and delete, and is always sorted. So that is a binary search tree. Hopefully you're familiar with BSDs by now. The downside is, well, it's always sorted. So if you wanted it to retain the order that things were inserted in, you can't use a vector instead or something like that, or a queue or something. But logarithmic time, pretty good. Logarithmic time is pretty good. Constant running time is better. And you might think, like, okay, it's got to be kind of impossible, right, to do constant running time? Wrong. So, unordered set. Unordered set is a hash table. You might hear me on Discord sometimes saying hash map, because there's a YouTuber who loves hash maps. It's the Java term for this. C++ doesn't call it a hash table. It calls it an unordered set. Yeah, mostly because it was a name that nobody was using, because it's a dumb name. But it's not a dumb data structure, although it is kind of, it's not well implemented. It gives you order 1, insert, search, and delete. Has no order. Downside. So what does that mean? Order 1, insert, search, and delete. It's amortized time. It's possible that it might take longer occasionally, but those times that it takes longer are rare. So it averages out to constant running time. So if you have 1,000,000 elements in a hash table, or 1,000,000,000 elements in a hash table, if I ask you, is the number 72 in that hash table, it can tell you in, on average, 1 operation. Yes or no? You can insert things into the hash table in 1 operation. You can delete things from it in 1 operation. You can see if something's in it in 1 operation. Which sounds impossible. All right, it sounds impossible. I've seen those videos, now you understand. Yeah. Yeah. And I'll play one for you in a little bit. So how do these things look? What do they look like? Let's do a little code for them. So let's say we're just keeping a set of like, let's say we're just having like a set of numbers that we want to write down if we've seen them before, right? Like maybe these are student IDs, and if somebody ever enters like a duplicate student ID, we like get mad at them, right? So we can do something like this. Like we can do set of integers named Sito, and we can do like a while true loop or something, and do int ID equals read. Please enter a student ID 0 to quit. And we can say seto.insert the ID. And that will put the student's ID in there. But we want to check to see if it's in there first. And so we can do this. If seto.contains, contains is C++ 20. If you don't want to use C++ 20, you can use count. It's basically exactly the same. Account ID. I like the word contains better. It kind of makes more logical sense to me. But .contains is C++ 20 only. So if it already contains this ID, we are going to die or something. I don't know. It's or we could just be like cout that ID already exists. Something that's either in a set or not in a set. If they're in the set, we get mad at them, and maybe we'll just continue. We'll just reject, you know, the thing, notify the person you got a duplicate or something. I don't know. And otherwise, we will just insert it into the thing, and then when we're done, we will cout all of the things in the set. So we could do this for int x and seto, set x, just like that. And I always save, compile, test my code every 5 or 6 lines of code, always. So let's enter 10, 20, -10, -20. If we type in -20 again, it already exists. If we type in 10 again, it already exists. If we type in 30, it's a new one, -30, 42, 420, 420, already exists, done. Uh-oh, forgot that one. Just logged out. So yeah, that's why you always test your code. I forgot the break statement, right? Always test your code for that exact reason. So if we type in 0, if not ID, break. There we go. Always test your code. All right, 10, 20, 30, -30, -20, -10, 0. And you see that when we print everything in a set, it is always sorted from least to greatest. Make sense? So the nice thing about a set is it is always sorted. Sometimes you just have a requirement that all of the data that you have is always in alphabetical order or whatever, and there you go. So if you're going to be printing it out a lot, and you're going to be printing out a lot in sorted fashion, set is great. Okay. Now, faster than a set is an unordered set. Okay. And that's it. All I had to do was change set to unordered set. Everything else is the same. The interface is the same. Don't, like, that's it. All I have to do is recompile. And now, if I do the same thing, what do I have? 10, 20, 30, -30, -20, -10, 0. You will see that the numbers do not come out in any particular order. Right? It's like, it's not really sorted, right? It's not the order I typed them in. Or maybe it is. Maybe it's the order I typed them in backwards. It happens sometimes, but there's no guarantee of that, right? An unordered set is unordered. You know, if you're trying to emulate like a line at a bank and you need people to be served in the order they arrive at the bank, you use a queue for that. You don't use an unordered set, or a set for that matter, because the set would like organize them by like first name or whatever, right? So if you need the order that they arrive to be preserved, you would use a queue. Okay, different data structures for different jobs. That's the name of the game. Okay, so you need to know all of the basic data structures. Then when somebody hands you a problem, you're like, that's the right one that I need. Oh, you need it to be printed out, sorted a lot, huh? How often? Like a lot? Okay, I'm going to use a set then. You know what I mean? Like the needs of your customer, or you, if you're your own customer, you know, determines which data structure you use. That's what CSI 41 is all about, and it's an essential thing to learn as a computer science major. What about like a relational database row of data? Yeah, databases are a very complicated data structure, and when you go into junior level classes, you can choose to specialize in it, and you got to learn how databases work. Relational databases, you have to choose certain fields to be keys, and what they do is they generate a data structure so you can search on the key very quickly. So why does a normal set have logN search? Is it ordered during a search? I understand the sort being imposed at insert and delete. Because you are doing a binary search tree lookup, right? So if you are searching for So if I tell you, hey, find the number 14, right? You start at the root, go to the left, go to the left, go to the right. That's logN time. If you have a balanced binary tree, which the set class is. It's a balanced binary tree. Okay. BSDs are terrible if they could be unbalanced. So there'd be really no benefit of using a BSD if you could have them be unbalanced. So it's basically logN, insert, search, delete. Okay, so the unordered set is faster, but how much faster? Let's find out. Do you guys know how to time stuff? Time it out? Yeah, we can do that. But I'm going to show you kind of a better way of taking timings. Yeah. Okay, so we're going to just time like doing 1,000,000 inserts into like a binary search tree. Okay. So we could do it. Using time. G++ -03 main.cc. Actually, let me do this with no aliases turned on, just in case I have some weird flag set up. So if I run this with a size of 1,000,000, time a.out, and it's timing me right now. I feel kind of judged right now because the slower that I type, the longer it's going to take to run, right? So that took 9.8 seconds. You see that? The time spent actually was 1.1 seconds. Okay. This is actually the amount of CPU time used by the program, and this is the time spent in the system, in kernel calls and things like that. This is the wall clock time. So the actual running time was 9.8 seconds, but a lot of that was just because I was sitting there staring at it, right? And so yeah, this is okay. This is an all right way of timing things, but this whole thing, like I feel judged whenever there's a stopwatch running and I've got to type, forget about it. So I could like redirect input into it, but there's a better way. So let me show you how to do. So here's learning point 1 for the day. Set versus unordered set. Okay. And learning point 2, let's capitalize the P, how to do timings in C++. Normally I do a queues project where you learn this kind of stuff. Instead, I'm just going to kind of show you. So, because we're doing a lot of debugging right now instead of having you guys do the timing stuff. So there's the C way of doing it, and there's the C++ way of doing it. So I'm going to show you the C way, and that is just to say this. There's a function called clock, and clock gives you the number of microseconds since the program began. I actually kind of prefer the C way of doing timings to the C++ way of doing timings. You are free to disagree with me, but let me show you. So this thing is technically of type clock T. You can just use auto instead if you want. It's fine. And so that tells you the number of microseconds that it's been since the program began. So you're essentially starting a stopwatch at time equals 1,000 or something. And then you stop the stopwatch, auto end equals clock, after your loop is finished. So we've done 1,000,000 inserts or whatever. Stop the stopwatch, subtract the difference, cout end minus start in microseconds. And there you go. That's it. So if we started at 1,000,000 microseconds and ended at 3,000,000 microseconds, it'll say this took you 2,000,000 microseconds. Makes sense? Yeah? I'm actually kind of a fan of the C way of doing things, even though it's not as good as the C++ way. simplicity of code has its own beauty. You know, how much time does the ctime library add? Very, very minimal. So if we do this, compile it, and run it, then it tells you how many microseconds it took to run. Okay. Just copy paste this. You can run it a couple different times. Usually when I do timings, I do like 5 runs. You know, it depends how accurate I want to be. You can either take the minimal time, or you can take the average time. Depends on what you want. The minimal time here was 0.934 seconds. Okay. And if you want this to be expressed in seconds, you can divide by 1,000,000, basically. So, yeah. Let's see what the difference in timing is between set and unordered set. Okay, just one change. One simple change that doctors hate. And we run it again with a size of, shouldn't have selected that, 100, 1,000,000. Okay, good. And so you can see the hash table is about twice as fast. Okay. Bit more than twice as fast. One change. Change it from set to unordered set, and my code is now twice as fast. You assign that time to a variable and use it if you wanted to. Yeah, I mean, if you wanted, you could just, these are just ints, basically. It's just an int. So you just like cout start. And that is the number of microseconds since the program began. And so you can see it began the stopwatch at 1,342 microseconds since the program began. And then it ended 409,000 and change microseconds later. Okay. So it's just in it. So the clock function, man clock, you can just see it returns just returns in it for you. Okay. Or whatever clock t is. This thing will wrap around every 72 minutes, so that's a problem. Like I said, the C++ fashion is better. On a 64-bit system, clock t is probably 64-bit. It's probably not that big a worry. But it is something you have to pay attention to if you're on a 32-bit system. Now, let me show you the C++ way. And the C++ way is step 1, open up cppreference.com. Step 2, copy the code. Step 3, paste the code. And the reason for this, and I'm actually not even like being that sarcastic. I'm being a little sarcastic, is because the C++ implementation for timing stuff is completely superior from a technical standpoint. From a human usability standpoint, it's garbage. And I'll show you what I mean in a second. So I like using high resolution clock. I think it's actually an alias. Yeah, it can be an alias for one of these other clocks. But I like high resolution clock. It gives you the best. Precision when doing timings. And so let's see. We go to now here, and here's some sample source code, which we're going to copy and paste. And the reason why I'm going to copy and paste it is because, well, you'll see in a second. Okay. So copy. All right. So that. Let's pull these two things out here. Okay. Set. Okay. So there we go. You can see the difference in size, right? In the amount of typing you have to do between the C version and the C++ version. The C language, I think, has been infected by Java, honestly. Like, I think that a lot of people who have been working on the C++ language started on Java and just really like how verbose Java is. Java is a stupidly verbose language, and so why type 10 letters when 30 will do is the modern C++ philosophy. Not a big fan. If you want, you could use namespace Chrono and cut that down to size a little bit, but I'm just going to leave it in there for the sake of making a point. So that starts your clock, this ends your clock, and then you can't just print out a clock. It doesn't have an overload for printing. which is also kind of ridiculous. Instead, you have to create a duration variable here. And if you think I remember this every time, no, I copy and paste it every time because it's a lot of typing. Like, to me, this is a sign actually of a bad API. Like, if somebody has to Google something every time they want to use it, to me, that's a sign it's not well designed. Like, I always think to myself, like, can I show this to my CSci 40 students? You know, if I show my CSci 40 students how to roll a random number, you know, the proper way in C++, not the C way of doing random numbers, but the C++ way, can I show it to them? And the answer is no, not really. It's stupid. Like, how they do timings is just kind of dumb. How they do random numbers is it's technically competent. It's technically better. It gives you better precision. It allows you to convert it to all sorts of different time formats and things like that. It's great. It's just my perspective as a professor is, can I show this to my first semester students? And if I can't, it's not well designed. Okay. So we got this, and then we cout diff.count, and this will give us seconds by default. .43 seconds. Okay. Same answer, just with a different timing method. Okay. So, to be perfectly frank, like when I'm doing my own work, a lot of times I just use the C way. You know, as long as your code's not running for more than 72 minutes, you're fine. And this is on a 64-bit system anyway, so it should be fine also. Any questions about this? Don't allow my bias to like infect you, by the way. Like, if you're actually writing professional code, you should be using Chrono. It's just better in every conceivable way. Just like how C++'s random number generation is better in every conceivable way than the C way of generating random numbers. It's just not a well-designed API. That's the difference. Okay. This you can teach to a CSci 40 student. This, they're not going to remember it. Yeah. Okay. Any questions about that? How to do timings? You don't have to remember it. No, I literally Google it every time. Just like every time I need a random number in C++, I Google it every time. Have you guys seen random numbers in C++? Like the C++ way of doing it, not like the RAND and SRAND kind of way. Like, anytime you expect a first semester student to remember MT19937, it's not good. It's not well designed. I'm sorry. I'm sorry. Yeah. So you create a random device, you create a generator, create a distribution, and then you can call that distribution passing in the generator. So there's like multiple steps of setup to get to the point where you can just roll a random 1d6. Apparently this is changing. So this is something I've been like kind of complaining about for years, and apparently they're actually going to finally just give us a random number for 1 to 6 function, which would be amazing. That it's actually useful for new students. So why is it named that? It's Mersenne Twister 19937. What do you mean? Why is it named that? It's yeah. Like there is like zero chance. Like if I put a CSI 40 student in a blank room and give him a midterm and said all you have to do to pass the midterm is make a random number from 1 to 6 using C++, not rand, srand, which is memorable. You can memorize that. Nobody would pass that midterm. Yeah. Okay, so blame the French. All right, so that is that. Okay, so unordered set, unordered map is the other thing we need to talk about. So let's talk about the difference between map and set. Or not set and map. Yeah, set and map. Okay. Set versus, sorry, not that one. Okay, there. Let's move this down to here. Okay, learning point 4. Should use a set or a map. So what's the difference between a set and a map? Okay, so for a set, the value and key are the same. Wait, what does that mean? Okay, so let me show you how a map works first, and then you'll understand the difference. All right. So if I make a map, and I map it between a string and an int, I'm going to call it mapu. I can insert things into this. I'm gonna show you the bad way of doing it first. Okay, so mapu January equals 31. February has 28 days. So if you've ever used Python, JavaScript, Lua, they have these things called associative arrays. Okay, and it works like an array, except rather than the array index being 1 or 5 or 0 or whatever, the index of the array is the first thing here, a string. Okay, so I am writing to the array at array index January the value 31. Okay, so January is the key. The key locates the spot in the data structure where the value is found, and I'm saving the value of 31 there. So for a set, the key and the value are the same thing. When you insert into a binary search tree that we've been doing so far, okay, that's not what I was looking for. Here. It's like if I insert like 27 into this tree, the key, which is what we're using to navigate through the tree, and the value, which is the thing we're saving into the tree, are the same thing. Make sense? So go to the right, go to the left, go to the left, save 27 here. For a map, the key and the value are different. So you might use an integer to save yourself into the tree, but the thing that you write there might be a submarine or something like that. So for example, you could have a map between an int that's like somebody's social security number and a person, if I had a person class. And then I could find people in the database using their social security number, and what I actually write, the data that I write to the tree at that social security number is, you know, a person, which is like, I don't know, like a name, address, you know, yeah, all that stuff, right? Hair color, you know, does that make sense? And so you would use their social to look up the person and to save them into the tree, and that's what it would sort them on. It would be sorted by social security number. But the actual data in the tree would be like, you know, height and weight and name and first name, last name, middle name, you know, all that kind of stuff. So flashbacks to the Pokemon assignment, or the ELO assignment, yeah. So sets have, the value and the key are the same. Yeah, the value that you insert is the key that they use to put it into the tree. They're like maps, but just simpler. Okay. Yeah. Okay, so this is the simplest syntax for a map. This is dangerous syntax, though. And the better way of doing this, this is called the danger syntax, okay? The better way of doing this is to do something like this instead. Mapu.insert, passing in April and 31. And you might notice some weird syntax here. I'm passing in a single parameter to the function. And what I'm passing in is actually two values. One is the key, one is the value. And so maps work on something called a pair. So let's talk about pairs for a second. So pairs are actually defined in the utility header for some weird reason. And a pair is a templated pod, basically, plain old data, that can take any two types. So you can have a pair of like a float and a string or something like that, named P, and set it equal to 3.1415 and Bob. Okay. So I've made a pair, and it's doubly templated. It has its first parameters of type float, second parameters of type string, and if you want to access the elements of the pair, it is p dot first and p dot second. All right. So the reason why I'm mentioning this is because maps work with pairs. You insert a pair, and when you, there you go, 3.1415 and Bob, and I forgot to do the end line there. Let's just run that again. So you can see we're getting 3.1415 and Bob. So the first element in the pair is dot first. The second element in the pair is dot second. All right. You like pairs? Yeah, they're kind of tasty. Pair jam's really good too. Think of the social as a label for the memory address, and the actual value stored there as a person's name, something like that. Yeah, something like that. So, yeah, the reason why pairs matter is because that's what you work with when you work with a map. You insert a pair, and when you search it, you get a pair back, always. And that's why I kind of like working with sets better, because it's like one less thing. You know what I mean? It's one less thing to worry about. So this is learning point. What are we down to? 5 or something? Pairs. It's probably going to bother some people, huh? Okay. So, the better way of doing this is we insert a pair containing the key value pair. Okay. It's a little bit redundant. All right, that's the better way to do it. And do I eat it or code it? Kind of hungry. Yeah. Yeah. When I was in Providence, I had a pear upside down cake that was chef's kiss, fantastic. Had a little bit of blue cheese on it. So good. Can you go out of bounds like an array? So this is actually kind of okay here. Like, this is not going to get you into any trouble. All right. The danger syntax isn't actually here. It's actually here. You might ask, like, why is this dangerous? Well, if you're writing things into the hash table, it's actually fine. It's actually not really going to cause any problems. It's when you're reading from it that the danger syntax causes problems. So, if I were to output mapu square bracket January, I get 31. Okay? Probably what you expect, right? So you can insert into this associative array a value associated with a key, and then later on you can look up the key and get the value back. Okay? Order 1. Very, very fast. This is an incredibly powerful data structure, and I'm going to play a meme for you in just a little bit before I give you some lab time. So, the reason why this is dangerous... here, let me do something else. Let me show you how to print a hash table first. So for every pair of string integers named p in the hash map, cout p dot first and p dot second. All right. So I'm just going to print out everything that's in the hash table. All right. So here we go. We got April, February. You see they're in no particular order, right? So this is the contents of the hash table. Everything looks fine. We're getting 31 out of January. Okay. Now, let's say that I screwed up and I typed in January. All right. Simple mistake. Perfectly valid C++. This isn't a compiler error. It's not an out of bounds error, technically. It's a What do you think this is going to print? There is no entry for January. What is it going to print to the screen? It's got to print something, right? Or is it going to throw? Compiler error? Syntax error? Seg fault? What's it going to do? It's going to create a January and see out nothing. Prints out 0, which is troubling, but okay, I guess it's got to print out something, right? But look at what happens here. Look at what just happened. It inserted January into our hash table. All we were trying to do is print it out, and it added an entry for January and gave it a value of 0 and then returned 0. This is not good. This is very, very, very not good. Okay? So whenever you're looking up things from a hash table, don't use square bracket. Okay? Or if you do use square bracket, you always have to check to make sure that it exists first. So there's a couple of different ways we can do that. One thing we can do is use .at instead of square bracket. .at January. Or let's just make it May. Why not? May. And if it doesn't exist, then rather than inserting into the hash table, which is almost certainly wrong, and it's going to cause all sorts of troubles down the line. You know, you try searching for somebody, they don't exist. Now there's an entry for them in the database. Oh Lord, this is not good. This is really not good. Rather than doing that, it will throw an exception, right? If you try searching for Aunt May, and May is not in the database, it throws an exception and kills your program. That's probably preferable. The way that I usually use it, though, is I do this. I say if mapu.contains May, print how many days are in May, and then I could just use square brackets, of course, if I wanted. Yep. And this is safe. Because I'm checking to see if it existed before. Okay. So if it exists, I can echo it. If it doesn't exist, see out. Not A, not found. Okay. So, didn't find May, and notice now it's not inserting May into the hash table. So you have to be very careful when using square brackets. If you really want to be safe, combine both. It's going to be probably a little bit slower, but whatever. You can do both like this. You can both check to see if it exists, and then use .at just in case you happen to type a different word here and here or something, right? So it'll print Aunt May not found. Now, again, contains is C++20. If you're doing earlier versions, you can do mapu.count. Another way you can do this is to, so this is inserting into a hash table, searching hash table. So a couple different varieties of inserting here. Searching a hash table. Another way we can do this is say if, well, we can do this. Auto iterator equals mapu.find. So let's search for February. If I can spell it properly. Okay. So find is another way you can search it. Again, this is order 1, right? This is extremely fast. Hash tables are an extremely fast data structure. They are my favorite data structure out of all the data structures in this class. They're my favorite because there's just nothing that compares to them for speed if what you want is inserting, searching, and deleting, which is the most common operations, right? You put people into a database, and then you say, all right, let's find, let's look up our customer. You know, you type in their social, record appears instantaneously. The DMV probably uses a vector and searches from the beginning to the end. That's why it takes 5 minutes for the record to come up. Okay, so another way to do this is called find, and then if you remember how find works in the standard library, it returns a iterator to the end if it's not found, which looks a little weird. That's why I kind of prefer this. And count kind of bugs me too. I use C++20, so I just use contains. Okay, so if it double equals mapu dot end not found, cout feb not found, else cout it points to second days in February. Or actually, it points to first if I wanted. Yeah. So remember, everything with a map is a pair. So when you search it, it returns two things. It returns the key and it returns the value. Now the key you already know because it's right there, right? So you technically don't need to, it's February, right? But like the second is where the actual data is being returned to. So yeah. So if we just compile this and run it, maps are great. They really are. They're kind of a fundamental data structure in most programming languages. So like in Python and JavaScript and Lua, like you just like in Lua, I think all arrays sort of are associative arrays. By default, if you make an array with indices 0, 1, 2, 3, 4, 5, it's fine. It'll actually make it as a traditional array. But you could just be like array square bracket 5,000, and if it's not contiguous with the other elements, it turns it into an associative array. And it will use 5,000 as a key, and then it'll store whatever you want to store there. And you can use anything as a key. You store a string as the key, whatever, and it will just associate whatever you want with whatever you want. Use so much dictionaries in Python. Maps are not ordered, I'm pretty sure. So maps are ordered. So maps are ordered. Unordered maps are not ordered. Okay. And so a map is a binary tree. An unordered map is hash table. And I was doing the wrong one because it doesn't matter. The interface is exactly the same. Right? Sorry. What I had before was actually a binary tree. You won't see the difference, though, because the interface is exactly the same. A map and an unordered map have exactly the same interface. The unordered map is going to be faster. The map is always going to be sorted. And it just depends which one you want. Okay. Unordered maps are even faster. Yes. Absolutely. Unordered maps are what I use as my data structure. Like, that's like vectors and unordered maps are my go-to data structures. They're my two go-to data structures. Yeah. you guys with me? Like vectors are just my vanilla ice cream. Like I just need to hold some data and just put them into a vector and whatever. But when I want to have fast saves and lookups and things like that, unordered map every time. We all did ELO last time, right? Last semester. Not everyone was in my class, so I'll show you the code for it. So I have an unordered map that uses a ID and a person, right? And then I read in the name and address and all this kind of stuff and create a competitor out of their name and address and ID. I then check to see if they're in the database. If they're in the database already, we die. If not, we add them to the database. And technically, this is going to insert them into the database. But because I'm dying, right, it doesn't matter if they're already there because it won't insert them. And if it did just insert them, I immediately overwrite it. So technically, even though this is Danger, Danger, Will Robinson, it will create very briefly a competitor in there. I then immediately overwrite it. So I could have used .contains there instead. And then, I don't know, .second, you see that? That's the, right? So everything in a map is dot second is where the actual data is, right? So I just go through the entire hash table, push the value into a vector, sort it, because you can't sort a hash table, right? So what I do is I take all the elements in the hash table, put them into a vector, sort the vector, and then print the winner. So vectors and unordered maps are my chocolate and peanut butter. Like, that's all I ever eat is chocolate and peanut butter. Okay. That's you know, we learn a lot of data structures in this class, lists and stacks and queues, and I can just tell you from what I actually use, vectors, unordered maps, that's not 100%, but it's like over 90% of the data structures I use. Okay, so let's give you a homework assignment. So the homework assignment is going to be this. A little bit of lab time, and then we're going to finish the class on a completely different topic. Okay? So I'm going to give you a little bit of lab time to work on this. And what you're going to do is this. You are going to, given a target and a vector of integers, return the index of the two integers in the vector that add up to the target. Okay. So for example, target is 42. The vector is 10, 20, 30, 40, 50, 1, 2. It returns index 0, index 1, index 2, index 3, index 3, index 4, index 5, index 6. Okay, 3 and 6. So indices 3 and 6 in the vector add up to 42. 0, 1, 2, 3, 4, 6. Yeah, 40 plus 2 is 42. They're not sorted, and you want to be able to do this in order in time. Okay. The brute force approach would be a doubly nested for loop where you check every number against every other number. It's order n squared. A faster version of doing it is sorting the vector, and then you can walk in from the edges. For example, you'd start with 1 and 50, and then you could walk inwards on it until you hit 42. It's order in logN to do it that way. But if you use a hash map, you can do it in order in time. By what you do is you write down every number that you see, and you write down its index. And then if you ever see a number that, like when you get to 2, you subtract 42 from 2, you get 40, you say, hey, have I ever seen 40 before? Oh, I have. There it is. There's the answer. So when you get to 30, you check to see, hey, have I ever seen the number 12? Right? Because 42 minus 30 is 12, right? Nope. Okay, move on. And so you either check, so you do two things. You check to see if its complement is in the hash map. If it is, you win. If it's not, you add the number to the hash map. Move on. Okay? So I will play a YouTube video for you. There is a YouTuber. I'm sure some of you have seen this guy's stuff. He's really funny. Yeah, this one. So I'm going to pause the stream so I don't get copyright struck, but I'll play this, and it basically will make the point that you should always use a hash map, if you need speed, and it's true. Like honestly, between vectors and hash maps, that's that'll do over 90% of all the stuff you need. Okay, pausing the stream now, and then I'm going to resume the stream once lab time is over. And we are back. Hopefully you had enough time to work on that. Copy this thing up. There. And I'm just going to comment this all out. So up in /public/map.cc, you can find all the source code for today. I'm just going to do this thing here. So we'll do int value equals read. Please enter the target value. This is actually a common enough job interview question. It's not just from that YouTube video. Mick Corelli found it in cracking the coding interview during the previous class. And good. All right, so you're just doing that. I'm actually going to do a little loop here. I'm actually going to just input it from the user. X equals read. Enter a number. 0 input. vector images effect. That's a 0, we break. Otherwise, we add it to the vector, and we will just test the code now and make sure that it prints properly. File, run, whatever, 10, 20, 30. Okay, cool. Done. Always test your code. Every time you finish like a little block of code, test it. It's good practice to be in. Really struggling with this? Well, that's what lab time's for. It's get the practice in. All right, so try it. Interesting. Okay. Yeah. So now we need to find if any pair of numbers will add up to the target. Let's call this target. Target. All right. So we will do this in a for loop for int I equals 0. I is less than vector.size I++. It's going to be mad at me for not using a size t, so I'll just make this an int, whatever. I don't care. Just shut up the warning. Or I could use a size t for I, but I'm going to be inserting it into a hash. Whatever, it doesn't matter. Okay, so unordered map between an int and an int. Okay. I'll tell you mapu. Shut up. If you're stuck, ask for help. Yeah, that's the difference between in person and online. Like me and Carly and I were walking around together, looking at people's screens. When we're in person, online, we can't tell. You know, I'm just posting funny memes on Discord. So you're trying to avoid the order n squared algorithm so bad. Yeah. Your copy of Cracking the Coding Interview comes in. Yeah, it's a good book. It's a really good book. It's not too expensive either for the size. It's actually quite reasonably priced. Okay. So what we want to do is we're going to get int current is equal to vector dot at I. So we're going to get a value. And we want to see if the complement is in there already. So the complement of a number is equal to the target minus the current. So if the target is 40 and our current number is 10, the complement is 30. So what we want to do is see if 30 is already in the hash table. And if it is, we win. If it's not, we add the current number into the hash table and continue. And then if we ever find the complement to us later on, then it'll find us, right? So like if we're 30 and we haven't seen a 10 yet, then we just add 30 to the hash table, we move on, and then if 10's down the line, it says, hey, have you ever seen 30 before? The hash table says, yes, you have. And then you need to pull out the index that it originally was. That's why we're using a map. The first int here is going to be like 40, and the key is the value, and the value is the index, something like that, if that makes sense. Okay, so have we seen this? Have we seen the complement before? So if mapu.contains complement, then we win. Okay, so see out. So we just want to see out the current index that we're at and the index of our complement, and that can be found by just mapu complement and comma and I, and we're done. If not, then we will add our current value to the hash table. So mapu, I'll just use square brackets because it's safe when you're writing to it. And square brackets is safe here because I'm using contains first. If you want to be more cautious, use dot at there. So mapu.current is equal to I. So I'm going to save my index into the hash table using the key of its number, basically. And if we get through the whole thing, see out, no pair found or whatever. And that is a quick little solution to a pretty normal coding interview problem. So target value is 42, and we've got 2 and 10 and 30 and 40 and -10, -20. So index 0, index 3. There it is. Okay. Oh, perfect. Okay, so that is that. And what is the not a complement? I'm not complimenting you on your code. A complement is right. So if we're trying to add up to 100, if I'm looking at 53 right now, the complement is 47, right? It's the matching number, because we're trying to find two numbers that can add up to 100. So if I'm at 53, what I need to know is there a 47? If there's a 47, they add up to 100, and we're done. Because we're not doing like any combination of numbers. It's just two numbers, exactly two numbers that add up to 100. And so if I'm currently reading the number 53 here, then all I care about is, have I ever seen the number 47 before, the complement? And the hash table will tell us that in order one time. Yes or no. And so if the answer is yes, then we look up the index, because that's what we saved. What we did was we saved the index of 47 into the hash table. And if we did not find it, then we just write down our index into the hash table. So for 53, we save our index, whatever it is, in the hash table, so that if 47 comes up later, we can pull it out of the hash table and print them to the screen. Okay. If you didn't care about the indices, then you could do this whole thing using a unordered set rather than an unordered map, and just print out 47 and 53 to the screen. Okay. So complement is, yeah, when you do subtraction or whatever. Like multiplication and division are complements to each other. Okay, so you like your cut G. What is a cut G? Your cut G. It's a meme. Okay. I see.
You playing Minecraft. I like your cut G.
Gotcha.
You playing Minecraft.
All right. Gotcha. All right. All right, so let's move on to the last topic of the day. And the last topic of the day is software development. And you got Chrono to play the video. Yeah. Oh no, I played a meme. All right, so let's see here. There we go. So we'll talk a little software engineering today. All right. So your next homework assignment is going to be doing something called TDD. Min Curley requested it. We've been doing a lot of debugging recently, and he thinks it's really important for you all to get trained on TDD. So that's what your next homework assignment is going to be. It's an easy homework assignment. You've done fizzbuzz before. This is just fizzbuzz again, done using a TDD mindset. So what the hell is TDD? TDD is called test-driven development. The basic idea of TDD is that you write your tests first, and then you write your code, and your code should pass your tests. And if that sounds kind of similar to like what you do with your homework anyway, it is, and it's not accidental, because I've been sort of secretly ninja teaching you test-driven development. Now you're going to get to do it yourself for this homework assignment. So let's talk a little bit about how old school software development works, and by old school I mean people still do it this way. So let's say you're given a year to design and implement a product. Okay, so let's say that New York State comes to you and they say, hey, look, we've got this problem with our time card system. People are swiping their friends in when they come into work and swiping them out, and some of these people don't even come into work and we're paying them full time. So we need you to implement a biometric time card system. Okay. So in the traditional, what's sometimes called waterfall development system, what you do is you sit down with New York State and you get their requirements. All right, what exactly do you need? All right, we need to make sure that people are actually there and not, their friends signing them in. Okay, so eyeball scans, fingerprints, what are you looking for? And you get all that kind of settled with the client, your customer. you sit down and you write down a design doc, a specification, and what it does, it says everything that you're going to do for them, right? We're going to build out software that we're going to build a box, and the box has a fingerprint reader and an eyeball scanner on it, and the software is going to connect to a database, and the database will authorize them and write down when they signed in, when they signed out, that kind of stuff. And this design doc or specification documentation is actually really important because that's usually what translates into you getting paid. And so this old school of doing software development isn't necessarily that outdated because, you know, a lot of software projects are paid on milestones, right? So when you meet this milestone, you get released a certain amount of money. And so having a design document usually turns into milestone X, milestone Y, milestone Z, and the money kind of gets portioned out to you as you do that. So these things are still important, even though this waterfall method isn't highly recommended anymore. You then have 3 months out of the year to implement the code, 3 months to test it, and then you deploy it. You go to the hospitals around New York City, you put in your boxes, whatever. You know, as you roll it out, you kind of keep an eye on things, make sure things don't break, and then you debug it over time. And typically, one of these contracts that you sign has a maintenance guarantee kind of thing. Like if you find a bug in it in the first 48 months, then we will fix it for you for free. After that time, if you want us to continue bug fixing the program, it will cost $5,000 per year, whatever. Okay, come out with a service contract or something. If the boxes break, then, you know, it costs $100 per service visit for us to send out a person to fix the box or whatever. Okay, pretty normal. And typically, though, like customers will over time be like, all right, it's cool and all, but could you add in, like, I don't know, nose detection or something? I don't know. And you're like, all right, that's not really a bug, that's more of a new feature. And so over time, you sort of gather up enough requests for, you know, what about lunch breaks? You know, can you temporarily pause? You know, like they'll come up with new requests, and you're like, yeah, that's not really part of the debugging schedule set of things. Small features you might implement, like if somebody says, hey, you know, this doesn't work on, you know, people wearing glasses or something, you might have to actually sit down and write code, you know, and get it to work with glasses or something. But like in general, like anything that actually requires new development is you charge for it. You either quote them, hey, if you want us to add breath detection biometrics, I don't even know if that's possible, that'll be $50,000, you know. Or you kind of bundle up all of these feature requests and say, all right, we'll do version 2 for you. Version 2 for you will cost $5 million. And you go through the whole process again. Okay. So that's sort of an idealized way of doing software contracting. It doesn't actually work in practice very well. And the reason why it doesn't work in practice is because, for a lot of reasons. First of all, your customers don't know what they want. They think they know what they want. They actually don't know what they want until they've seen it, right? So if you have a design document that says we'll do X, Y, and Z, you do X, Y, and Z, they hate it. Now, you might get paid, and that's very important. That's why these design documents are actually pretty important, because even if they hate it, they still got to pay you. But then they hate you, you know, and so there's a downside to that, right? And so it's much better to not expect people to be able to know what they want in advance, because usually they don't. They have some idea, right? But as development takes place, you know, things change. Like you realize I can't do this, you know, and the same goes for your specification document. You say we're going to connect to a SQL database. Maybe you decide to use MongoDB instead or something. You know, like you don't always know which database solution is going to be the fastest until you've got something going, and then you test it, and you're like, okay, this product's actually better, and you switch. You know, you call an audible and mix things up and stuff like that. So this little waterfall methodology is kind of it's kind of garbage. Okay, and the reason why it's garbage is because you have to plan everything out like a year in advance, and plans never go according to, you know, schedule, or you know, life never goes the way you expect it does, you know, especially in software. And so there's a different methodology called Agile, and Agile involves, like, you meet with a client, you get an idea what they want. Okay, you want us to do biometric. Okay, and so you hack up a prototype like really fast. Like you make a cardboard box, and it's got like a piece of paper with crayon on it, on the cardboard that says like fingerprint reader, and it's got like I don't know, like a thing from a kid's like binoculars, and that's the eyeball reader, and you like send it to them. You're like, hey, does this about look like what you want, you know? And they're like, no, that's horrible. You can't put the fingerprint reader and the eyeball next to each other. I don't want dirty finger balls next to dirty eyeball. You know what I mean? Like I don't want people's hands touching, where my eye's going to go. Okay, cool. And then that allows you to call an audible really early, and then you just make another mock up and you send it to them. And basically every week you work on a little bit of it, and you get something releasable every week. And every Friday you push it out to them, and then they look at it over the weekend. And then on Monday you get the feedback from them, and they say, we hate this, we like this. And you work on the most important features first, and you're very quickly knocking products out, even if they're just cardboard boxes at the beginning, or just mock-ups or a little web page with a Microsoft Paint picture on it, just so that you can get their feedback early on when it's easy to move things around, rather than after you've already wired up this box and they're like, we don't want the fingerprint reader next to the thing. And then all the wire, like everything like has to get redone, and it's very expensive to change things at that point. So Agile involves quick releases, 1 week cycles, and also 1 month cycles and things like this, where you're like quickly knocking out products and getting feedback and iterating very, very quickly. And a lot of the world has moved to Agile. Even hospitals use Agile now. They do the different parts of Agile. Agile is like a big thing. Biometric urinals, yeah. And so the the hospital that my wife works at, they do stand-ups. Stand-ups are an Agile thing where at the start of every week, everybody stands up and has a meeting. You stand up because you can't get comfortable. If you're sitting down in a meeting, you got donuts and stuff, people just sit there and talk forever, and you're just sitting there like, I need more coffee. I need more coffee. No. Meetings are one of the absolute worst things about being a programmer, let me tell you. They're just, oh man. They'll call you in for a meeting like anything. You're just sitting there, you're like, why am I here? Why am I here? They might ask you one question, and you answer it, and you're there for like 2 hours. And your soul is just so slowly separating from your body, and you're just like, don't fall asleep, don't fall asleep, don't fall asleep in front of the president. No, I'm going down. Ah! It's the worst productivity killer. One of the worst morale killers is meetings, and sometimes they're necessary. And so, with Agile, they acknowledge the fact that meetings are good for everybody to get on the same page, understand what everybody's doing, and so they have a stand-up meeting. You can't sit down and get comfortable. You can't waste 20 people's time for 2 hours, which is an entire week's worth of time. It's 40 hours a week, for one meeting. Right? And so you do stand-ups, and everybody kind of says what they're working on that week. You do your stuff for the week, and at the end of the week, you do another stand-up, and everyone says what they did. Just so that everybody's on the same page. I know that Bob's working on this. I know that Mincarelli's working on this. And I know who to talk to. Because actually having meetings when everyone's engaged, they're actually good. So there's an all-to-all communication. But most meetings devolve into one person having a conversation with one person for an hour, and then there's an entire conference room full of people that are sitting there just wishing to be elsewhere. One really good metric is, could I replace this meeting with an email? And if the answer is yes, it shouldn't be a meeting. If all they need me there for is to find out what the cost of this graphics card is or something, send me an email and I'll respond to you, and then I don't have to be there for 2 hours to answer a question. And they don't tell you okay, that was all we need you for, go. I mean, some people would, I guess, but yeah, they'll just keep you there, and you're just like, no. Yeah, meetings have banned all professionals' existence. My brother complains about this all the time. Yeah, they're horrible. It's one of the biggest wastes of times. The only time they're useful is when everybody's actually engaging with everyone else, because sometimes you just need everybody in the same room so they're all on the same page. You have a whiteboard and say, this is the architecture. Everyone gets to look at it. Everyone's doing feedback. You can parcel it out to different people. Meetings aren't all bad, but they're mostly bad. Okay, so waterfall is bad because it attempts to predict the future, and the future never goes the way you think it does. Agile is about responding quickly to the present. And so this is a great graphic from the Chaos Manifesto, which is one of the big things in Agile. And you can see how successful projects are in waterfall versus Agile, computer science. Free food's the best part. Yeah, usually, like at my places, they do like free like donuts and stuff. But here's the thing: like after you've had your first free donut, like the second donut and the third donut and the fourth donut are just like, no, it's not good. It's really not good. You know? Oh. So, pasta tutor training today in Reedley. Nice. Yeah, free pasta I'd go for. Yeah, but like free donuts, like a donut is like my limit. Like after that, I feel just disgusted with myself. You know, like what am I doing with my life as I'm just shoveling donuts down. Krispy Kreme is so oily. Yeah, I can't deal with Krispy Kremes. It like one maybe after, like I just feel bad about life after eating one. Free steak with grilled vegetables, I'd go for that. Yeah, sure. Yeah, if you have a lunch meeting, like that's another thing. Like you feed me, like I'll be there all lunch. Yeah, sure, yeah. Give me a stupid sandwich and a cookie and iced tea. Like sure, I'll sit there. Working lunches, like I didn't mind because then I don't have to pay for them. You know what I mean? Like, you're working in an office and there weren't any restaurants like near us. We had to like get in a car and like drive a ways. Like sure. You want to do a working lunch? I'm all for that. Sure, yeah. Buy me lunch. I'll sit there all hour. And I don't have to clock out either because I'm working too. So, yeah. So here we have the success rates of Agile versus Waterfall. So Waterfall, of all the big software projects in the world, has a 14% success rate, which is terrible. It's really, really bad. There is no other industry that would accept success rates of 14% like this. You know what I mean? Like if you go to like buy a computer and you have a 14% chance of it arriving, nobody would tolerate that. Okay, sure. Challenge means it's over budget or over time, right? It's like sure, you buy a laptop from Best Buy. You have a 14% chance of actually getting your laptop on time and on budget. You have a 57% chance that it comes in a year late or at twice the price. Nobody would tolerate that. And 29% of the time, you don't get a laptop at all. You get a bag of Legos, and they said, hey, we tried making a laptop out of the bag of Legos, and we couldn't. So, sorry. Thanks for the money, though. We appreciate that. So, software engineering is just a weird world. Okay. So, let's move on to TDD. So, TDD is the notion that you write your tests first. Okay. So, you write tests for your code. If you're writing a function to compute compound interest, you say, all right, given this principal and this interest rate and this, it's compounded hourly or monthly or whatever, this is the amount it should be, okay? And you create a bunch of those. Like you just run through the math on your hand, and you just calculate, given these inputs, this should be the output. You create the tests first. And then what you do is you run the tests on your code. Your code should fail all of them. That's good. It's really good if you fail your tests. If you create a bunch of like compound interest tests, and you haven't written it yet, and your code's just returning 0 or whatever, and you test it and they all pass, you screwed up your tests. There is something really wrong with your tests if you pass them all before writing code. Maybe every so often you'll pass one because one of the answers should be 0 or something. But and you're just stubbing out your code with like a 0 or something. But like by and large, you should have all red to begin with. Red is the color of a failed test. And then as you write your code, the test will start passing, right? And if this sounds like the input tester for the homework you've been doing for the past year, yeah, it's intentional. I've been doing TDD with you, kind of, except I write the tests instead of you writing the tests. And that's a weakness that I'm trying to resolve with this homework assignment. So with this homework assignment, you're going to write the tests, okay? And test writing tests, and debugging are two skills that are really important in computer science that have sort of atrophied on a lot of my students because I do it all for you, Like your code doesn't work, you send it to me and I'm like, oh, there's the problem, Testing, well, just run the input tester, There's all the tests. And so a lot of students haven't developed the ability to test their own code. or to debug their own code. And so that's what I've been trying to work on this week and into next week, is like kind of building those muscles up. Okay. So one of the important things when you do these test cases to think about edge cases and error cases. So for example, an edge case is like anytime you have an if statement, you want to check the numbers like on the if statement and like one up and one down, right? So if you say the interest rate can't be higher than 10, right? You're going to test the code at interest rate 10, interest rate 10.1, interest rate 9.9. If you're near max integers, you test around the boundary there as well. So you check for overflow and things like that in your code. And then there's error cases. For example, if your code's not supposed to take negative numbers, test it with a negative number. See if your code handles the negative number properly, right? And then there's weird edge cases like POW, right? If you're doing POW, nobody knows what the POW of 0 to the 0 should be, right? Because any number to the 0th power is 1, but 0 to any power is 0. So what is POW 0, 0? Nobody knows, And so if you're writing a POW function, like you got to figure that out, write it down in the test somewhere, right? Because it's a weird edge case, like it's a paradox, like nobody knows. And so, you just put it down, like, okay, we're going to define POW 0, 0 to be 1, which is what it is in the standard library. If you do POW 0, 0, it gives you 1. So, Kearney will not always be there to write your test cases. Yeah, that's what this upcoming assignment's about. So, yeah, anything that's weird like that, you need to put a test case down for that as well. Okay? And then all these tests form what's called your test suite. And so your test suite runs on your code. And you can see how many tests you're passing. Those are green. You see how many tests you're failing. Those are red. And if you have like, big sad, yeah. If you have like your GitHub and all that stuff set up integrated properly, you can make it so that like if you push code to GitHub, to like, at a real company, right? You push your code, compiles your code, runs your code on the complete test suite. And if any new tests fail because of your code, it kicks it back and does not accept it into the repo. That's pretty common, right? But here's the good thing about that. That can actually make you very confident, right? Because most of the time when you're working with coding, you're not starting from a blank file like we're doing all the time. You're going to be working on a project that has 1 million lines of code in it, and you just never know if you change something, if you're going to break somebody's code somewhere, right? Like a lot of times the bugs in the code get enshrined, right? Like if you say, oh, look, there's a division by 0 there, and you fix it, somebody's going to knock on your door the next month and be like, yo, I needed that floating point exception. I have this code, and it's an infinite loop, and it just terminates when it gets a floating point exception thrown by that function. And because you fixed the function and it doesn't throw anymore, my code now infinitely loops. It's your fault. That is very, very common stuff, actually, where bugs are just like, people start relying on the bugs and make it Kearney AI. That's funny. And so what you can do if you have TDD is you're like, look, your thing didn't require a floating point exception to be thrown, right? And if you don't have a test case for it, you can't yell at me. The test cases define what is correct. And that's something that's really nice. The test cases define, it's a definition of correct. And they also give you what's called a definition of done, right? So you actually know when your code is finished when everything turns green. A lot of times in computer science, you don't know when you're done. You don't know when you're done because you just kind of always keep working on things forever, Like, keep testing it, maybe you'll find some more stuff. But with TDD, once you pass all the test cases, like this from your homework assignments, all test cases passed, done, send it, go home, go play video games. That's it. And so with red-green refactor, which is a term in TDD, you start off, everything's red, you work until everything's green. That's your definition of done. If you have good test cases, when everything's green, you're done. And then you typically spend a couple days refactoring your code, cleaning it up. Oftentimes your first pass at things is kind of ugly. Maybe you speed it up, you put in a hash map, or something like that. You refactor it, but then a lot of the times when you refactor stuff, you break things, right? And so you can check, right? You refactor the hash table, you rerun the tests. Oh, I got a red. Oh, shoot, I forgot. I'm not handling a 0 anymore, and then you fix it. And so one of the really nice things about this is that it gives you the confidence to refactor, because if you are passing your test cases before, you refactor, you pass your test cases after, you're good. And so you can actually feel brave and confident in fixing bugs and fixing things because you've got your test suite will tell you if you screwed up. And so TDD is great. It's not universally applicable. It doesn't work very well with like video games and things like that. But basically, it gives you confidence and it gives you a definition of done, which is very, very important. So it does slow down build time. Sometimes, you'll have 10,000 tests. And so a lot of times the testing runs overnight and you find out the next day that you broke something, right? And sometimes you make one small change and you break all the tests because you have an off by one error or something, right? And then you don't know what you did, everything's failing now. You're like, what did I do? Maintaining the test takes time. Oftentimes tests have to be updated, right? When you change your code, you have to change your tests, right? We're now allowing negative interest rates or something. Like you have to update your tests along with your code. And it's really hard to do GUI stuff. It's hard to do video games, things like that. So it's limited, but it's very, very useful. So your homework assignment is something called fizzbuzz TDD. And you've already run fizzbuzz once. You're free to copy and paste that code. It's A-OK. Fizzbuzz isn't the challenge. Okay. So what you're going to do is you're going to write a function called fizzbuzz. And fizzbuzz is going to take in a number from 1 to 100, and it's going to return a string. And so it returns the string fizz if it's a number divisible by 3, buzz if it's divisible by 5, fizzbuzz if it's divisible by 15, error if you return a number that's less than 1 or greater than 100. But if they pass in a number like 17, you just return the string 17. You use the toString function. Okay, and that's fizzbuzz. Now, that's not really what the assignment's about, though. You should do it, but it's not really the assignment. What the assignment's about is about making tests. Okay, so this is a macro. It's part of the Google Test Suite, the GTest suite. Okay, and so the Google Test Suite is going to be testing fizzbuzz, and the name of this block of tests here is called good tests. And what you want to do is create a test for every kind of good value, like 3 and 30 and 50. You don't have to do all of them, just representative. Make sure that it exercises every branch of the code. Make sure you got one for a fizz and one for a buzz and one for a fizzbuzz and a couple for regular numbers and things like that. Just create a good scattering of tests between, I don't know, I'd say 5 and 10, something like that. Okay. And then you're going to do bad tests. So bad tests are bad inputs. For fizzbuzz, anything less than 1, anything over 100 is bad. You probably don't need too many of those, just at least 2. One for negative territory, one for positive territory. That's about it. It's not going to be too hard. And then for the edge cases, remember what I said, an edge case is when there's a boundary. And you want to kind of test the numbers around it. So test 0, 1, 2, 99, 100, 101, and make sure that those are being handled properly. Okay? And then you're going to do the same thing for fizzbuzz 2, the next iteration of fizzbuzz. And so fizzbuzz 2 is actually very similar to fizzbuzz, except you add the digits together and do a fizzbuzz on that as well. So 23 is going to be buzz because 2 plus 3 is buzz. So you have to add the digits, and otherwise it's exactly the same thing as fizzbuzz. And I'm going to want you to make your own tests for fizzbuzz 2 as well. You are going to be auto-graded as far as correctness on the program, but you're also going to submit screenshots. You're going to submit 2 screenshots. One is going to be of all of your test cases, and the other is going to be, when you run it, you can run test here. And this is actually the test suite running. You can see we're failing some things here. We're calling fizzbuzz with a value of 3, and we're getting fizz as the result. Oh, sorry, we're supposed to get fizz as a result. Sorry. We're getting empty string as a result. So that failed. We got a red. Okay? And then here we're passing a negative 50 to fizzbuzz. We're getting empty string as a result. Should have been error. Fail, fail, fail. So we're getting all these reds. So what I want from you is 2 screenshots in addition to the auto rating stuff. One is a shot of your code, your test code. The other is this, but it passing all the things. It should look something like you need to make your code with make as well. So this is what it'll look like when you pass all the test cases. Okay. So everything's green. Okay. So that is your assignment. You have till Wednesday to do it. It's not a whole week because it's an easy assignment. Yeah, it's really not a hard assignment. I was thinking about making it due on Monday, but yeah, this should just be a free 10 points for everybody in the class. Okay. Fizzbuzz, you've already written, and just you're going to learn how to do TDD with the GTest suite. Okay. And Mincarelli is a big fan of TDD. I'm a moderately good fan. I'm not super sold on it just because I do a lot of game development and stuff like that. It's not as useful in game development, but it's important to learn, especially because a lot of people hire based on TDD stuff. So it's everywhere in the industry these days. Not universal, but you see it just in a lot of places. So this will be a good experience for you using Google Test Suite, which is a real suite. It's not like a toy thing. Yeah, so it'll be good for you. It's not hard. It's 10 points in your pockets. And if you have any questions, just ask me on Monday, and we can pick it up from there. So that's it for today. Ash is going to be giving a workshop in the workshop channel. So if you guys want to pop on over into there, we'll be talking about resources available to students, and we will call it there. All right, thanks a lot.